Good day to you. PTQ Magazine and Digital Refining are pleased to bring you this webinar featuring Honeywell UOP. My name is Ken Mulway. I'm going to be acting as your facilitator today. I'm going to turn things over to Bill Blasco from Honeywell UOP. So Bill, you can take it away.
Thank you, Ken. Hello, my name is Bill Blasco, and I'm the Hydrogen Senior Offering Manager for Honeywell UOP. And welcome to the webinar on Honeywell CO2 and H2 Solutions. So first, we will talk about our CO2 solutions or technologies. UOP is the world leader in carbon capture technologies with our solvent, membrane, and absorbent technologies, and has been supplying these in carbon capture for greater than 70 years. The vast majority of CO2 captured is in the natural gas industry, and the CO2 is released to atmosphere because typically that has been accepted. But it's the same technologies that are used in carbon capture and storage applications. Today, UOP has installed CO2 capture technologies that enables greater than 33 million tons per year of CO2 captured for sequestration using the suite of technologies. One of the biggest installations that we have designed is to capture more than 30 million tons per year of CO2 and is located off the shore of Brazil, where UOP's Seprex membranes have been deployed to separate CO2 from a natural gas stream and sequester that CO2 for enhanced oil recovery, or EOR. We also have carbon capture and storage projects in gasification applications as well. Now, I want to briefly mention that UOP was announced a couple of months ago as the technology provider for a very large clean hydrogen project that's happening in the United States, in West Terre Haute, Indiana. The customer is a project developer. They are called Wabash Valley Resources, and they have purchased an asset, an old clean coal plant, and they're going to retrofit it with the gas water shift and carbon capture equipment to enable this asset to produce clean hydrogen. It will be UOP's technology that will be doing both the carbon capture and the hydrogen purification for this project. It's our cryogenic CO2 distillation technology for carbon capture and our pressure swing absorption technology for the hydrogen purification. This project is important because of a few things. First of all, the scale is very large. It's 1.7 million tons per year of carbon dioxide, which is very large in terms of carbon capture projects. And the carbon dioxide will be sequestered permanently underground in a saline aquifer. But perhaps most importantly is that it's demonstrating commercial viability of these types of projects. There are federal tax credits available in the U.S. for doing carbon capture projects, which is called 45Q, and this project's finances are based fully on these federal tax credits. So it's demonstrating to others in the United States that these types of projects are actually commercially viable, where they have always been technically viable. UOP has a broad range of CO2 solutions that have historically been deployed in pre-combustion CO2 capture. As mentioned already, UOP has been in this space for more than 70 years. Some of these technologies are in the chemical solvents area. Where you will be most familiar with is our amine technologies, both MEA-based and activated MDEA-based, and our bent field technology. We also have within our portfolio our advanced solvent for carbon capture, or ASCC, where the formulation is designed for post-combustion CO2 capture. I will dive into more details on this technology on the next slide. In addition, we have numerous examples of CO2 capture in the syngas space, where typically our physical solvents have been deployed, such as our Separol technology. In natural gas treating, we have our Seprex membrane technology and cryogenic solutions. Then finally, we have our pressure swing absorption systems, or PSA, to purify the hydrogen by rejecting the CO2. As I mentioned, we have our advanced solvent for carbon capture, and this is currently being developed for flue gas carbon capture applications. Flue gas carbon capture is one of the most challenging carbon capture sequestration applications because CO2 is available at low partial pressures, and it's harder to extract from the process streams. Also, with the fact that flue gas has oxygen in it, and often other oxygenates and SOx and NOx, and those can be very hard for solvents. We have done extensive pilot plant testing of this solvent and are currently looking for our first commercial application. The advantages of this solvent is its high mass transfer rate and proprietary internals. This allows us to make the absorber and stripper columns smaller, therefore saving in CapEx. In addition, the low heat of regeneration minimizes the steam required for the solvent regeneration. Finally, the enhanced thermal stability allows us to run the stripper at higher temperature and pressure, which saves a stage of compression in the CO2 compressor, so we have additional CapEx and OpEx savings. So for natural gas combined cycle flue gas applications with USGC pricing, our advanced solvent carbon capture technology provides 20% lower cost of CO2 capture over other leading flue gas CO2 capture technologies. Now let's move on to our Honeywell H2 Solutions. I believe most people are familiar with this graphic, but for those that are not, I would like to take a moment to show everyone where we are today. Hydrogen production is not a new market. Currently, about 75 million tons a year of pure hydrogen is produced globally, primarily for the refinery and agricultural market. Where most of that hydrogen is produced from natural gas and coal via steam methane reforming or gasification. Along with that high purity hydrogen that we're producing, the process also generates more than 800 million tons a year of CO2 that is released into the atmosphere, roughly 10 times that of hydrogen. So although hydrogen can be burned as a fuel and generate no CO2 emissions at that point, we must find a way to cost effectively produce that hydrogen with much lower CO2 emissions. Demand for low carbon intensity hydrogen is expected to increase close to tenfold from the 75 million tons per year produced today to 550 million tons per year by 2050. As it replaces natural gas, diesel, and jet fuel in the so-called hard-to-decarbonize sectors, such as industrial, residential, and heavy transportation. Reducing emissions in these sectors requires either large-scale and distributed deployment of carbon capture sequestration or switching to renewable or clean burning fuels. Hydrogen is a promising fuel because it generates no greenhouse gas emissions at the point of use, so hydrogen is going to be used in different areas than where it is used today. This chart from the Hydrogen Council shows one vision of that surging hydrogen economy, where hydrogen will be 18% of the world's final energy demand by 2050. Other agencies have projected even higher numbers, up to 24% of the world's final energy demand. But reality will hinge on our ability to deliver clean hydrogen solutions at a viable price point. So let's briefly talk about the different colors of hydrogen and how they are produced. Gray hydrogen, which is largely practiced today, is the production of hydrogen from hydrocarbons without CO2 capture, essentially emitting the CO2 into the atmosphere. However, if you capture the CO2 instead of releasing it, this is blue hydrogen, essentially the addition of carbon capture on gray hydrogen production. Then you have green hydrogen, which is the production of hydrogen via electrolysis of water using renewable power. While the cost of green hydrogen is expected to fall, low carbon hydrogen produced using CCS or blue hydrogen is and will remain the most commercially viable option in the near term. Even under bold assumptions on electrolysis, blue hydrogen will continue to be a cost-effective solution, particularly in regions where large sources of low-cost renewable electricity are not available. I would also like to note that the CO2 intensity is roughly the same between blue and green hydrogen. So how do we see blue and green playing out? While the future of green hydrogen is bright, and we believe the cost of electrolyzers and renewable power will eventually come down, blue hydrogen is ready now. It offers a lower cost, and it uses commercially known and proven technologies. The main hurdles for blue hydrogen is the widespread development of carbon sequestration facilities for permanent geological storage. There are currently many worldwide projects in various stages of project life cycles, amounting to approximately 40 million tons per year of CO2 storage capacity. However, if by 2050 all of the 550 million tons per year H2 demand were to be met by blue hydrogen, it would generate about 5 gigatons of CO2 per year. This CO2, however, would then consume only less than 0.02% per year of our current assessed global high and medium confidence underground CO2 capacity. Ongoing development of CO2 infrastructure for transportation and sequestration is definitely needed in tandem with blue hydrogen and other CCS decarbonization projects. But the good news is that if we do invest in that, there are plenty of reserves and capacity for the CO2. So this is what a blue hydrogen plant will look like. You have your carbon feedstock coming into your traditional reforming gasification technology. Then you come to a technology where you can capture the CO2 at high purity, which will be ready for sequestration and utilization. And also producing a high purity hydrogen project, which can be used across all kinds of sectors: industry, buildings, transportation, and power. Or the hydrogen can be transported via pipeline, or for long distance it can be liquefied or transported via ammonia. It utilizes proven technology to convert hydrocarbon feedstocks, including renewable feedstocks, into synthesis gas, and then separate that syngas into hydrogen and CO2. I'm going to spend the rest of this presentation talking about blue hydrogen as the ready now technology for decarbonizing hydrogen production. For blue hydrogen producers aiming for carbon intensities approaching that of green hydrogen, they will need to choose among 3 hydrogen generation processes: steam methane reforming technology, or SMR, that is optimized to minimize radiant firing while using a hydrogen-rich stream as fuel; autothermal reforming, ATR, which contains the exothermic partial oxidation chemistry to fuel the endothermic steam methane reforming reactions; and partial oxidation chemistry. Each one of these methods can be used to convert hydrocarbon feedstocks into synthesis gas. I'd like to note a few differences between these technologies, which will impact the selection of our carbon capture technology. In an SMR, there is both a process gas and a flue gas. Both of these streams contain CO2. The process gas stream contains CO2 produced from the water-gas shift reaction. The flue gas stream contains CO2 from the burning of fuel to heat the reactor. The shifted process gas stream contains about 15% CO2 at roughly 20 to 30 bar pressure, whereas the flue gas stream contains a little more CO2, maybe 8%, but at roughly ambient pressure. This lower pressure makes it significantly more challenging and more costly to capture the CO2. In an ATR or POX reactor, the flue gas stream is eliminated. Now all the CO2 is concentrated in the high pressure process gas stream, making 90+% CO2 capture from the overall hydrogen plant easier. However, this scheme also needs oxygen as a feedstock. For the talk today, I'm going to focus on pre-combustion technologies applied to the steam methane reformer or SMR technology flow schemes. However, these technologies can also be applied to ATR and POX technologies. Let's first cover the traditional hydrogen production flow scheme. This is a gray hydrogen flow scheme, where natural gas is fed into the SMR hydrogen production unit, which makes a syngas, which is then shifted to convert more of the CO into CO2, and then sent to a hydrogen pressure swing absorption unit, or PSA, to purify the hydrogen. The low tail gas stream from the PSA unit, which contains the impurities, including CO2, is then sent to the SMR burners as fuel, which natural gas as the trim fuel, and it is burned. So all the carbon from the natural gas exits the SMR from the flue gas. To reduce CO2 that is emitted, it can be captured from three areas: the syngas upstream of the hydrogen PSA unit, the tail gas of the hydrogen PSA unit, or from the low pressure flue gas. The cost of CO2 capture depends upon the pressure and concentration of the CO2 in those streams, but it also depends on the product specification for the hydrogen and the CO2. The most cost-effective location to remove CO2 is from the pre-combustion streams. The CO2 can be removed by a variety of ways, including solvent-based absorption, pressure swing absorption, or cryogenic fractionation. Let's now review those technologies in more detail. But first, I want to mention that there are other means to reduce the carbon footprint of the hydrogen production. The first you see on this slide is the use of bio-based feedstocks. The use of renewable feedstocks can reduce the life cycle emissions and is an important tool for hydrogen producers to leverage where that is available to them. Pre-combustion CO2 removal technologies will reduce emissions by up to about 60% in a traditional steam methane reforming flow scheme. So for a typical refinery, SMR producing 100,000 tons per year of hydrogen, up to 520,000 tons per year of CO2 can be captured, which is a large amount. But to further reduce those emissions, CO2 must be eliminated from the flue gas stream as well, and there's two ways that exist to reduce those flue gas emissions. The first is solvent-based post-combustion CO2 absorption, and the second are steam methane reforming revamp options or design options if you are building a greenfield plant to minimize the furnace firing and use a hydrogen-rich fuel in the furnace. As the flue gas stream is really the most expensive stream to remove CO2 from, the current commercial solvent technology would cost 2 to 4 times more per metric ton of CO2 captured than pre-combustion capture. But the flue gas emissions, as I said, can be reduced through these steam methane reformer revamp options that can minimize furnace firing. These options include operating the reformer at a high methane conversion in a pre-reformer, a primary reformer, and even optionally a secondary gas-heated reformer. You can eliminate excess steam export. You can use a structured catalyst insert. And adding low-temperature water gas shift in addition to the traditional high and medium-temperature water gas shift can also be used to minimize CO content in the shifted syngas. Removing the pre-combustion CO2 would be a key enabler as well, and then finally diverting a slipstream of your hydrogen-rich fuel to the furnace. So I think the use of all of these measures, coupled with your pre-combustion capture, can result in greater than 90% CO2 captured without the need for the expensive post-combustion capture in a blue hydrogen flow scheme. But the best option for pre-combustion CO2 capture that provides the lowest overall cost is cryogenic fractionation, which also achieves additional high-purity hydrogen yield. In this option, the hydrogen PSA tail gas is compressed and dried, condensed, and fractionated, resulting in an ultra-high purity liquid CO2 stream, which is ready for sequestration or ship transport. Combining your separation and your liquefaction in a single unit operation saves utilities when a liquid product is required. With this option, you can also recover 90% of the remaining hydrogen in the PSA tail gas stream. So combining this additional hydrogen recovery with the hydrogen being recovered in the existing hydrogen PSA unit, you can achieve an overall 99% hydrogen recovery from the steam methane reformer. This additional hydrogen recovery goes a long way in offsetting the investment in the CO2 capture technology, actually reducing the net cost of CO2 captured to $20 to $40 per ton of CO2. The retrofit that I've shown here is differentiated in another way, and that it does not require a revamp of the existing PSA unit, and you can operate your CO2 capture technology on or off without impacting the steam methane reformer operation. Since the composition has changed of the recycled tail gas going back to the burners, a burner revamp is required, but Honeywell UOP's new innovations in this area have enabled burner technology that can rapidly switch between fuel sources if you were to operate with your CO2 fractionation system on or off. Other advantages of this solution is that it's solvent-free. It has a much smaller footprint than an amine unit, which we'll talk about in a second. It requires no steam usage, and it's guaranteed to meet high purity CO2 product specifications with greater than 99% CO2 recovery. Another option for CO2 capture from the hydrogen PSA tail gas is to use a CO2 PSA pressure swing absorption unit. The CO2 PSA option is the lowest CapEx and OpEx carbon capture option, and it can also remove 99% of the CO2 in the pre-combustion stream. This option is optimal when a less stringent CO2 purity specification is required. The CO2 product in this option is at low pressure. However, catalytic oxidation followed by drying and multiple stages of compression can be incorporated to make the CO2 product transport ready. The third option for CO2 recovery is amine-based solvent capture of the shifted syngas, and this is a flow scheme that's well established. It's known that it can achieve 99% CO2 removal from the shifted syngas. However, this option does have some drawbacks. For one, it requires the use of steam for solvent regeneration, and the carbon emissions associated with that steam generation erode the net benefit. In addition, by removing the CO2 upstream of the hydrogen PSA, the overall hydrogen recovery will be reduced. This reduction could be eliminated with the hydrogen PSA absorbent reload or cycle modifications. However, these modifications would make it difficult to continue to operate if the CO2 removal unit were bypassed. So typically, you wouldn't do these modifications, and you would then have to accept that 1 or 2% reduction in hydrogen recovery when operating with the carbon capture system online. But in applications where you know a producer may be low on steam or has a certain familiarity or preference with this technology, I think the solvent system application here is certainly a proven technology. And finally, we have our advanced solvent for carbon capture technology, or ASCC, to capture the CO2 on the flue gas of an SMR unit or the post-combustion stream. As I mentioned before in this webinar, this solution is more expensive than the other options presented due to the low pressure of the flue gas and partial pressure of the CO2 in the flue gas, but we can capture greater than 95% of the CO2 from the overall SMR. UOP is currently developing an advanced solvent for flue gas carbon capture, and we're looking for our first commercial opportunity right now. This technology, when commercially available, will have lower regeneration requirements and lower CapEx than the current commercially available flue gas capture technologies. The combustion equipment, essentially the SMR furnace and burners, are the engine that drive the hydrogen production. As I mentioned already, a review of the combustion equipment is therefore warranted and needed when considering retrofitting an existing steam methane reformer from a conventional hydrogen production operation to a decarbonized hydrogen production, since this will significantly alter the flue gas composition delivered to the SMR burners. With Honeywell UOP's combustion furnace and burner expertise and a history of successful partner experience with SMR furnace licensors, we are uniquely qualified and capable of doing this review. As part of a feasibility study, an inspection of the combustion equipment can deliver recommendations for maintenance and/or technology upgrades to enable decarbonized hydrogen production. UOP's Calidus proprietary CUBH burner platform technology provides consistent, stable, low NOx emission burner performance. And this can be achieved when the fuel is rich in CO2, when the CO2 capture technology is offline, and when the fuel is lean in CO2 but rich in hydrogen when the carbon capture technology is online. As the decade progresses, new blue hydrogen assets in the form of steam methane reformers, autothermal reformers, and POX reactors will be built to realize the potential of hydrogen to address these hard-to-decarbonize sectors. Escalating carbon price coupled with emerging technology advances will drive those investments. But there is not a one-size-fits-all solution for blue hydrogen. So by pairing your carbon capture and your hydrogen purification technology together with your hydrogen production technology of choice, economic differentiation can be achieved, delivering a significant step in the CO2 countdown to net zero. Some of the considerations include composition of your syngas stream, which is impacted by the choice of your hydrogen production technology and how you operate that technology. But also important to keep in mind is that your target purity of both your hydrogen and your CO2 can influence the choice of your capture technology. And finally, your access to utilities such as steam and low carbon intensity electricity could influence what is the best solution for a blue hydrogen producer. But in short, efficient and customized blue hydrogen solutions can be achieved today, and they can have a good return on investment. I would like to close on a broader note. Hydrogen economy is not just blue hydrogen production. We have engineers and scientists at Honeywell UOP working on all kinds of technology for the hydrogen economy, including technologies to drive down the cost of green hydrogen production and trace contaminant removal with green hydrogen purification from this green hydrogen production, which contains different contaminants than traditional gray streams such as oxygen and nitrogen. Technologies for point-of-use separation, such as hydrogen blending into the natural gas grid. And finally, liquid hydrogen carriers for long-distance transportation for hydrogen. So hydrogen is certainly an exciting area of focus for us here at Honeywell UOP. I want to thank you for attending this webinar, and please follow UOP on our website or customer portal or the following social media platforms. If you're interested in Honeywell's CO2 and H2 solutions, please contact your Honeywell sales account manager. I'm ready to take questions now, so I'll turn it back to you, Ken.
Thanks very much, Bill. Well, I am going to invite Bill to turn on his camera. We'll see if the technology feels like working for us. There he is. And we also have behind the scenes Eric Bennett and Brad Russell, who are helping out as well. All right, let's get into some of the questions. Bill, I'm going to start with one asking if clean hydrogen can impact the CO2 footprint of an existing refinery.
Yeah, definitely, Ken. Thank you for the question. Often a hydrogen plant is the largest point of source for CO2. So adding CCS or carbon capture and sequestration on a hydrogen plant can reduce those carbon emissions of a refinery by up to 20% or more in some cases. Thanks, Ken.
All right, great. Let's keep going. Question about what areas in the world does carbon structure infrastructure exist, and where is it still developing?
I can take that question as well, Ken. There's about 30 sites worldwide, mostly in North America, Europe, but there's also sites in Australia and China and South America. It's developing, and currently in many places, but fastest in those areas. what's really going to be challenging for the carbon capture infrastructure is the development of those sequestration sites, and that's what's going to have to keep pace with the amount of CO2 that we capture over the next decades. Thanks, Ken.
All right, continuing on. Is there a future for blue hydrogen after green hydrogen becomes inexpensive?
Yeah. Yes, green will continue to be expensive even after electrolysis costs come down in places in the world that don't have good access to sun and wind. So that's the areas where blue hydrogen will still be cheaper in those areas. And there are also lots of existing assets like steam reformer assets out there that can be retrofitted with carbon capture technology.
Great.
Thanks, Ken.
That leads me into a follow-up question right in the same area. This is a bit of a long sentence, so I'm just going to read it verbatim. We have different vintages and makes of existing hydrogen plants in our facilities. What factors should be considered when selecting which of these units might be best suited for retrofit for carbon capture?
Yeah, so UOP has experts and for evaluating your existing hydrogen production equipment, and we can take a look at it at the different hydrogen plants that you have and see what kind of revamping to maximize hydrogen production and CO2 capture. We'll do a feasibility study, which will inspect and evaluate the existing system and recommending maintenance and repairs and any upgrades and equipment that you will be needed for, a seamless transition from a conventional hydrogen production to a decarbonized hydrogen production with carbon capture.
All right, excellent. Here's a question asking about UOP Technologies, and this one is, does UOP have blue hydrogen solutions for ATR-based hydrogen production?
Yeah, our solutions for ATR-based hydrogen production are similar to the solutions that were shown in this presentation for SMR-based hydrogen production, because the syngas feed to our technology will have are similar in terms of quantities in general. UOP can offer a custom design for your hydrogen production technology, be it ATR, which is autothermal reforming, or SMR or POX. And we'll tailor that offering to the unique parameters of that hydrogen production design.
All right. We have a question here asking, what are the considerations for choosing SMR versus ATR or POX for a greenfield application? And we'll ignore O2 oxygen availability. And it continues, is POX with more than 95% capture going to be competitive with SMR with greater than 95% capture?
I can take that question. So one of the considerations for looking at SMR versus an ATR technology, right, has to do with size and scale. So, the ATR technology has a little bit more availability to scale to larger sizes. So the bigger the units you're talking about, the more preferential it starts to lean towards the ATR. And that's because of the partially because of the oxygen, the air separation unit required, but also because of the reactor design of the ATR and how that's different than the SMR, since the SMR has those tubular reactors. And so, that's part of it. Another consideration would be, inlet pressure of your natural gas, and higher pressures favoring, say, ATR and POX technology over an SMR. So if the gas is available at higher pressures, then that tends to lead towards that technology a little bit more, although not as much as, it doesn't have as large of an impact as the scale of hydrogen production. And as to whether or not POX with 90% carbon capture can be competitive with SMR with 95% carbon capture, again, I think that's going to lend itself to the scale. For very large scales, it may be possible that ATR or for larger scales, ATR POX type reactors may end up being more economical than the SMR. The SMR does have the advantage, though, of additional hydrogen production through the reforming process. So less downstream steps, smaller water gas shifts. So those are some additional considerations on comparing SMR to ATR.
Eric, stay on with me because I have what looks like a follow-up here. Somebody is saying, is there SMR technology commercially available today that could achieve percentages at the 95, 97, 98% level?
Yeah, so I think a potential solution for those SMR technologies, right, would be to look at CO2 capture on the high pressure shifted syngas stream, and then pairing it with a flue gas capture offering. And if you pair those two offerings together, it's more capex intensive, right? But that's how in an SMR you can get to that higher 90%, 97% plus CO2 capture. Alternatively, another option is to capture CO2 from your high pressure stream and burn more hydrogen. So again, it's a capex hit to the entire system. There will be a capex penalty because now you're creating or you're generating more hydrogen to essentially burn in your furnace. But that's another alternative that helps to improve CO2 captured from an SMR system to target those higher CO2 captured numbers.
Excellent. Here's a question asking about UOP service offerings. Bill, I think this one might be for you. Does UOP provide the service for an SMR burner retrofit, or is that outsourced usually?
No, Honeywell UOP does provide that service for a burner retrofit. As I mentioned in the presentation, our burners can, for a retrofit, can operate at the broad range of the fuel gas composition when your CO2 capture system is online and offline. Our burner group, which is Calidus, our burner group, which is Calidus, would probably work with the SMR licensor or the furnace supplier to make sure that this offering is ideal for the application.
Speaking of applications, I know you had a slide in here showing different potential destinations and uses of CO2. Somebody was just saying, it seems like you're dealing with a lot of CO2. Where can that go once it's captured?
Well, for CO2, it can be sequestered in the ground, or it can be used for an enhanced oil recovery. With our CO2 fractionation system technology, we can either provide it in a liquid at around we can supercool it to 7 to 10 bar, about minus 30 degrees C for liquid transport, or we can pump that liquid up to where it's where it's supercritical for pipeline transport.
Okay, great. Still looking for ones that seem like they would apply to a lot of people. Okay, this is going to be a long one. I'm just going to read it straight out. Get ready to take all this in. We anticipate needing to run in carbon capture mode for the foreseeable future. But what if economics or regulatory factors change and it's no longer commercially viable to capture and sequester CO2, or the CO2 separation equipment goes down? Will we be able to produce hydrogen in conventional SMR or PSA hydrogen plants if the CO2 separator is shut down?
Yeah, I'll take that question. Yeah, you'll be able to continue to still operate your blue hydrogen plant or your decarbonized hydrogen plant is going to be designed with our retrofit of the burners, or if it's a greenfield, we'll hopefully have Calidus burners on there. It's designed to transition seamlessly between the carbon capture technology being online and handling that fuel gas that doesn't have CO2 in it, and a conventional hydrogen production mode when it does have CO2 in that flue gas.
Here's a question asking, when would you choose ATR-based hydrogen over other production technologies such as SMR and gasification? What do you use as a criteria?
You want to take that one, Eric,
I
or
could take
Brad?
that one. Yeah, I would say
Okay.
scale. Scale is a big factor, particularly if it's a very large scale. You know, with ATR, you need oxygen, right? So you need an air separation unit, which is expensive. But an advantage of ATR is you're essentially, generating all the CO2 in situ, so you can get very high recovery, and it can be economical, especially at large scales. Yeah, thanks for the question.
Okay, thanks, Brad. What kinds of contaminants might you expect to see? And this person was asking about electrolytic hydrogen.
Yeah, I could take that one too. So for electrolyzers, you need to dry the stream, so water removal. And normally there's a small amount of oxygen, ppm level, up to maybe 1,000 ppm oxygen. Sometimes there's a little bit of nitrogen also. But we have technology to do that purification as well from water electrolyzers.
Okay, great. Here's a question about just the terminology we've been using, talking about blue hydrogen, green hydrogen, gray hydrogen. Are these standardized labels, or is it something that UOP is coming up with and imposing upon the world?
No, these are pretty much standardized labels where, you know, the blue hydrogen is essentially gray hydrogen production with carbon capture technology. And then the green hydrogen is where, you're using electrolysis and renewable power to power that electrolysis, and you don't have a CO2 byproduct.
All right, great. I am looking at our numbers, and people are starting to drift away, which tells me that it's time for us to let people get their cup of coffee and papers together for their next meeting session. So I'm going to go ahead and take the remainder of the questions offline. I have a complete log of everything that was asked. So on behalf of PTQ Magazine and Digital Refining, we hope that you found this webinar useful and informational. On behalf of Honeywell UOP and Bill, Eric, and Brad, thank you so much for your attendance today. Good day.